Hi guys, just wanted to do a screencast here of separating variables for Laplace's equation in spherical coordinates. As I mentioned in class, I'm going to hold you responsible for doing it in Cartesian, spherical, and cylindrical. Cartesian we did, spherical we're about to do, cylindrical I'll let you do on your own. Now when we do it in spherical coordinates, we start off with Laplace's equation written in spherical coordinates. And the book immediately assumes azimuthal symmetry so that there's no phi dependence. We're not going to make that immediate assumption. And so the process starts out looking the same. We make the assumption or the hope that we can write the potential as a function of r and theta and phi multiplied by one another, where all the r dependence is in one function, all the theta is in one, all the phi is in the other. And we plug that into Laplace's equation. And when we did Cartesian, then we divided both sides by this original function, and lo and behold, the variables were separated. In this case, it's a little trickier. We certainly are going to divide both sides of Laplace's equation by the potential. We're also going to multiply by r squared sine squared theta. And so if you plug this into here and you perform this operation, then you get the following result. And as you look at it, you realize that, the variables aren't separated. You think, well, I'll just divide by sine squared, but as soon as you do that, you end up getting a sine squared over here in the phi term. So up front, there's no way to separate the variables completely. But we're going to pull a little trick. If we look at this, we recognize in this last term, it is a function of phi only. So we have a function of r and theta plus a function of phi equal to 0. We can use the same logic we used when we did separation of variables in Cartesian coordinates to say, well, then each one of these individually has to be equal to a constant. And so in particular, then we can write this last term is equal to some constant. I'm going to choose the constant minus m squared. We could have chosen a positive constant. We could have chosen a negative constant. And the only reason to make it a squared is because I know where this discussion is going. Because the second derivative of phi with respect to phi, second derivative of the function with respect to phi is equal to a negative constant times the function itself. That means our function has to be sines and cosines. Hence the m squared just turns into an m inside the argument of the sine and cosine. More importantly, however, is the logic in choosing the minus sign. If we consider our spherical charge distribution, we know that the azimuthal dependence has to be periodic over a period of 2 pi. Because if we go around any spherical charge distribution, it doesn't matter the symmetry. If we go through a full rotation of 2 pi, we come back to our original position. And that means this function has to come back on itself. We can't change the value of the function as we go through a full rotation of 2 pi simply by, I just imagined that I went around my charge distribution, walked around it in a circle, and when I got back to where I started, all of a sudden, the value of the potential was different, even though I didn't change the charge distribution itself. So phi has to be periodic over a span of 2 pi, which screams out, hey, set this equal to a negative constant, and your phi dependence will come out to be periodic or sinusoid. That's not a small piece of information there. That doesn't come out of any mathematics. You have to be able to logic that out based on the reality of the world we live in. In other words, this is describing the potential of some static charge distribution. And if you imagine walking around that charge distribution such that you go through a displacement in phi of 2 pi, you know you're going to come back to where you originally were. And so the potential, at least the phi dependence, has to come back onto itself over a period of 2 pi. So you fully expect it to be a sinusoid. We also know that m has to be an integer. so that phi is single valued or a periodic function of phi, so m has to be an integer. And we can now take that result for phi, plug it back up into here, and let's see what we get. We plug back in for phi, and I'm going to divide by sine squared as well to get that sine squared out of the r dependence. And this is the expression that I get. And so now we have, here is a function of r, and this whole thing is just a function of theta. Yes, there is a hidden functional dependence upon phi, but it's now, if you will, hidden inside this little m, where m is itself a constant. And so now I have separated the variables, but I had to separate the variables in a step-by-step fashion. So it's a little different, a little more complicated than what we did for Cartesian coordinates, but it's still doable. And so now we're going to write out these functions for f and h, the functions of r and theta, and then we have to solve them, and our variables will be separated. Individually, once again, this function of r has to be a constant, as does this function of theta. Because if we find a value of r and a value of theta that give us 0, and then I hold r constant and just vary theta, if this changes at all, then this won't be 0 anymore, because as I vary theta and hold r constant, this certainly isn't changing. And so if they added up to 0 for r1 and theta1, then I hold r constant and I vary theta, and all of a sudden this function changes. They won't add up to 0. So individually, these two functions have to be a constant. And so that gives us the following set of functions where we've chosen our constant to be L times L plus 1. Here again, you think, oh, well, I never would have thought of that. That's okay. This is done, again, in hindsight. And so, knowing what we know, this is the choice that we want to have for our constants. We could have done C1 and negative C1. And ultimately, we would have looked back and said, wow, this would have been a whole lot less complicated in terms of the answer if we chose our constant C1 as L times L plus 1. And so as you get more comfortable doing these, you'll understand the choice of these constants. The bottom line is it's still just a constant. So solving these two expressions, not trivial. You could do the R expression just based on what you've learned in Theophys with a little bit of time. This one's a little more complicated. But in the end, if you solve these two expressions, and I won't hold you responsible for solving either of these on an exam, but if you did grind through it, then you would find out that your solution for r takes on this form, a r to the L plus b over r to the L plus 1. And your solution for theta is what we call the associated Legendre polynomials. And so hidden inside here are individual polynomials written in terms of the powers of cosine. And the form of those polynomials is determined by the values of L and M. Now you can look those up. I'm not going to list them here. You can find a table of them in Boas from Theophys, or you can look them up online. But they're just polynomials written in terms of the powers of cosine, and those polynomials solve this expression. And so when it's all said and done, our general expression takes on the form of another double sum. Forgot to mention it, but L, the stipulation up here is that L ends up having to be an integer. And here is our general expression with, once again, 1, 2, 3, 4 constants of integration, and then the two unknown indices for your associated Legendre polynomial. Now, for the sake of simplicity, we will typically assume azimuthal symmetry. Azimuthal symmetry simply implies that m ends up being 0. It's the assumption that Griffiths makes from the get-go. And so if we assume azimuthal symmetry, what that ends up looking like is that m has to be 0, hence you get the result from Griffiths. And our solution for the potential reduces greatly, because if m is 0, d drops out, c is absorbed into a and b, and your associated Legendre polynomials are replaced by merely the Legendre polynomials, and those are listed in your text in the table in Chapter 3. And so this will be the general solution that we will use for solving problems in spherical coordinates. Now, we have greatly reduced the generality of problems that we're able to solve by moving to those with azimuthal symmetry. But the only thing we're really missing out on is mathematical complexity. And so there's no loss of physics as we move from non-azimuthal symmetry to azimuthal symmetry. We just avoid some really messy mathematics. And so here's our general solution. And we also now, the Legendre polynomials are written in, again, these are going to be polynomials written in terms of powers of cosine. But the cosines themselves, of course, are orthogonal functions. And so as you might imagine, there's an orthogonality condition for the p's. It's written in your text, but I'll list it here. And that's if we integrate two of the Legendre polynomials over the interval from 0 to pi, the theta integral, you get 2 over 2l plus 1 Kronecker delta L prime. This also is going to reduce the number of problems that we're going to try to tackle, in the sense that you need your charge distribution to have some symmetry over 0 to pi so that you can do your integral over 0 to pi. If we end up only able to do an integral over 0 to pi over 2, all bets are off, and we'll see this on Monday, because we don't have orthogonality from 0 to pi over 2. So we need our functions defined in such a way that when we do our integrals, they run from 0 to pi. So once again, all that does is reduce the number of problems that we're able to solve using this technique. But we don't lose out on any physics. We're just losing out on some mathematical messiness. It's not as if other problems aren't solvable. In fact, I have one. Maybe we'll do one in class for fun, where you just have to whip out different conditions for integrating Legendre polynomials over intervals other than 0 to pi. But this is the orthogonality condition, and we're going to therefore limit ourselves to charge distributions with that type of theta dependence. Okay, that's what I wanted to go over. Please make sure you look over this, and if you have any questions about this derivation, you come prepared on Monday to ask those questions about where in here things didn't make sense. Because if I don't have any questions, we're just going to start doing some Laplace's equation in spherical coordinates problems on the board. Have a great weekend.